Hello and welcome to a lecture on light and air. I am Mukosifu Rupero from the University of Venda, and I will be taking you through this section as we work towards understanding why planet Earth is habitable. Now, light and air is a small section on the story of planet Earth's habitability, and it can be found on the second part of this hierarchy of models, wherein the static, atmosphere, and oceans are introduced to the bedrock model that we had previously. From the previous talk, we learned about Wien's law, albedo, and conservation of energy. We learned that the Earth is habitable not only because it is the right distance from the Sun, but also because it is the right size as well as color. We also learned that just a bedrock model of planet Earth would be too cold to be habitable. Now, light and air is a section amongst others helping us towards understanding why planet Earth is habitable. It is important because it brings about the static atmosphere and oceans to the bedrock model that we had before, and we explore how that contributes to planet Earth's habitability or the changes thereof. We will go over four major aspects, and that is light and air, where we'll explain what light is and what air is. We'll talk about what happens when light meets air, the greenhouse effect, as well as how all of this is linked to South Africa. Now, what is air? Air is made up of particles. Particles can be molecules, which in simple definition are a group of atoms bonded together, and examples of those are oxygen and nitrogen. Particles can also be aerosols, which are colloids of solid fine particles or liquid droplets, and examples of those are liquid droplets like water vapor and dust particles. From the kinetic theory of gases, air can be defined as a mixture of spread out particles that are in constant motion because of gravity. It is also because of gravity that small particles such as oxygen and nitrogen are found in the upper parts of the atmosphere, and big particles such as dust particles and water vapor are found on the lower parts of the atmosphere. We are going to use this later on in our talk. This is the pie chart showing the composition of air, and our air is made up of 78% of nitrogen, followed by 21% of oxygen, and the remaining 1% is a combination of other molecules and aerosols. Now, the Earth is surrounded by a protective covering or a layer of air known as the atmosphere, and it has got four distinct spheres, and namely the troposphere, the stratosphere, the mesosphere, as well as the thermosphere. The troposphere is the closest sphere to the Earth's surface and has just right temperatures to support life. In this sphere, temperature decreases with altitude, in contrary with what happens in the stratosphere, wherein temperature increases with altitude, as can be seen from this graph. Now, the stratosphere is preceded by a boundary known as the tropopause, wherein there is abrupt change in temperature, and that definition goes for all the other pulses as well, and that is the stratopause, which precedes the mesosphere, and the mesopause, which precedes the thermosphere. In the stratosphere is where the ozone layer is located, and although some of it can be found in the troposphere, most of it is found in the stratosphere from about 15 kilometers above the Earth's surface. It is important because it protects us from solar radiation from the sun while simultaneously insulating the Earth. Now, the mesosphere and the thermosphere are spheres wherein temperature extreme can be experienced, wherein you find that in the mesosphere we have temperatures too cold, and in the thermosphere we have temperatures too hot. So now that we understand what air is, let us explore light. Before I can say anything about light, I would like to start by saying that light cannot be ideally defined, rather scientists came up with ways of conceptualizing it. So even though you can see sort of a definition here, this is not really what light is exactly, but rather a way in which we can conceptualize or understand light better. So light is a transverse electromagnetic wave that can be seen by humans. It is part of an electromagnetic spectrum ranging from radio waves to gamma rays. It is found right in the middle of the spectrum and has one important property, that it can be scattered, reflected, and absorbed. So light is made up of a range of colors which form the visible spectrum. So the visible spectrum has a range of different colors, which range from long wavelength to short wavelength, and red has the longest wavelength in the visible spectrum, and violet has the shortest wavelength in the visible spectrum. I would like to repeat once again that there is not an ideal way of defining or describing light. Rather, we have ways of conceptualizing it, and that is why we have what we call the wave-particle duality. So the wave-particle duality is a concept that light can be modeled as either a particle or a wave. So Albert Einstein performed an experiment on photoelectric effect where he shone a photon of light onto a metal surface, and he observed that electrons called photoelectrons were ejected from the metal surface. Now this experiment by Albert Einstein served to prove or to model light as a particle. Also, Thomas Young performed an experiment on interference wherein he shone a light source through a slit, and he observed that as the light passes through the slit, it diffracted to form wavefronts. So this experiment served to model light as a wave. Now in the HPW course, we are going to be using light as a wave. So now that we understand what light is and what air is, let us explore what happens when the two meet. So when light meets air, it can get scattered, reflected, or absorbed. So first of all, what is reflection? Reflection is when light bounces off a surface. So for an example, we see the color of a typical leaf as green because green is the only color of all the colors of the visible spectrum that is bouncing off the surface of the leaf. Now absorption is when light makes it into a surface but fails to pass through the surface, so it is trapped in and the light energy is converted into heat energy. So it is important to know that the result of absorption is heat, because we are going to need this later when we're discussing the greenhouse effect. Scattering is when light collides with the surface and gets scattered in all directions. So in the atmosphere, light collides with particles both big and small, but small particles tend to collide vigorously with short wavelength light, and the light with the shortest wavelength gets scattered the most. Similarly, big particles tend to collide vigorously with long wavelength light, and the light with the longest wavelength gets scattered the most. I would like to repeat again that in the visible spectrum, red has the longest wavelength and violet has the shortest wavelength. So the knowledge of this and also scattering will help us answer this question. Why is the sky blue? I will answer that in 3 parts, and that is light from the sky, scattering, and being human. Now the light shines from the sun to the earth, and before it gets to the earth, it passes through the atmosphere. It is in the atmosphere wherein scattering occurs. So when we look up into the sky, we are looking up into the upper atmosphere where there are small particles. So we have already established that small particles collide vigorously with short wavelength light, and the light with the shortest wavelength gets scattered the most. So we see the sky as the color of light that is being scattered the most. So that accounts for the sky being blue. The big particles and long wavelength accounts for the sunset reds. So when we're looking at the sunset, we're looking into the lower atmosphere where there are big particles, and similarly, like we've already established, big particles collide vigorously with long wavelength light, and the light with the longest wavelength gets scattered the most. So similarly, even here we see the color of the sky as the light that is being scattered the most. So since in the visible spectrum, red has the longest wavelength, thus we have the sunset reds. However, in the part of the sky being blue, I emphasized that violet has the shortest wavelength in the visible spectrum. Why then don't we see the color of the sky, as violet and not blue? Well, the answer lies on the final part, which is being human. So this here is a graph that shows the peak wavelength where human eyes is best, and as you can see, violet makes for a small value in the sensitivity axis compared to blue. So what this means is that Even though violet is being scattered more than blue is, we as humans just can detect violet as well as we detect blue. So this picture here only serves to put emphasis on the fact that a human eye sees blue better than violet. So that is why we as humans see the sky as blue. Now that we got all that down, let us explore the greenhouse effect. The greenhouse effect is a natural process that warms up the Earth's surface. Now to explain that, let us revisit Fine's law, which was introduced in the previous talk. Fine's law tells us that objects of different temperature emit spectra that peak at different wavelengths. Hotter objects emit shortwave radiation, and colder objects emit longwave radiation. The sun is a hot body because it emits radiation of its own, and the Earth is a cold body because it does not emit radiation of its own. So from Fine's law, we know that the sun emits shortwave radiation and the Earth emits longwave radiation. So shortwave radiation is able to penetrate through the atmosphere without getting absorbed, and it hits the Earth's surface where it gets reflected back to the atmosphere. Of the reflected radiation, only 33% makes it back to space, and the remaining 67% gets reabsorbed by particles that readily exist in the atmosphere, such as carbon dioxide, methane, and water vapor. And like we've said before, the result of absorption is heat. So there is accumulation of heat in the Earth's atmosphere. This heating, however, is not lethal, but rather it helps bring the Earth's temperature from the negative 15 degrees Celsius that we had in the previous talk to temperatures that are suitable for life. This will be applicable also, however, if we had sort of circulatory systems to help distribute the heat evenly around the globe, or oceanic systems. But since we only introduced the static atmosphere and oceans, that is not applicable in this talk. So since we have more energy absorbed than reflected every time when the sun gives off its energy, the Earth would be too hot to be habitable to date. But that is not what we see happening. So that means that we have something missing, and we have to continue to explore to get answers. So now, how is all of this linked to South Africa? Well, South Africa has mountains such as Drakensberg and Table Mountain that make it possible to study changes in temperature relative to altitude. So let us review what we learned. We got to understand what light is and what air is. We learned that the color of the sky is due to scattering. We learned that the greenhouse effect is a natural process that warms up the Earth's surface. We also learned that with just the Earth's atmosphere and oceans, the Earth would be too hot to be habitable. So this suggests that something is missing. So be on the lookout for the next exciting talk on circulating atmosphere and oceans that will continue the search. Thank you.